composition, it gives a different microstructure. That means it gives a different phases. Phases represents the different kind of properties of those alloy. So just consider one alloy here given as a iron carbide. That means inside iron we are adding the carbon. Different percentage of carbon we are adding inside iron. And once it is heated up to its melting point, the melting point of iron is nearly 1539. And after converting it into complete liquid, we have started to cool it. So while cooling, we are getting different phases with respect to temperature and with respect to percentage of carbon also. That means as temperature is changed, there is a change in the phase. As percentage of carbon inside that iron carbide changes, again there will be change in phase. So those things we are studying, and that is nothing but iron carbide equilibrium diagram. Also, we have seen that why this diagram is called as equilibrium diagram, because for a constant temperature and for constant percentage of carbon in that alloy, the phase remains constant. The phase remains in under equilibrium condition. So that's why this diagram will become a phase diagram with equilibrium conditions. That's why this is also called as equilibrium diagram. So if you consider anything, that means consider temperature of 768 degrees Celsius. 768 degrees Celsius. So at that temperature, and if a percentage of carbon is zero, that means it is suppose pure iron. So up to that temperature, the phase of that ion will be alpha ion. Alpha ion. So that phase will remain constant. If suppose you consider temperature of 1147, if you consider this temperature of 1147 as a constant temperature starting from this to this, so at that temperature, if the percentage of carbon is 2%, at that constant temperature and constant composition, the phase will remain constant. At this point, this will be under solid condition. So above this, it will be having gamma plus liquid. That means it will be solid as well as some amount of liquid will be there. Again, at suppose 4.3% of carbon, again, and temperature 1147 is also under solid conditions. But if you consider the percentage of carbon as a 1% and this temperature as a 1147, so here phase will be different, and that phase is a gamma austenite, because here austenite is a solid solution of iron and carbon. Here also, whatever this portion, small portion we have seen, it is alpha ferrite. If 0% of carbon is there, it will be just called as alpha iron. But if it is a alloy, that means a composition of iron and carbon, some amount of carbon, that means up to 0.025% of carbon. At this temperature, you will get this alpha ferrite. Similarly, one more phase is there, that is a delta. That delta, if it is a pure iron, you will call it as a delta iron, and if it is a solid solution, or you can say just alloy of iron and carbon, then we will say this delta as a delta ferrite. So delta ferrite, gamma austenite, and alpha ferrite. These three, firstly we have seen in detail, these three phases are solid solution phases, and these are present in the solid state. These phases are the solid solutions, and these are under solid condition. Here we have seen liquid, that means the iron carbide, whatever we are looking for, iron carbide equilibrium diagram, that iron and carbon alloy will be liquid condition or liquid state in this position or in this area. Here it is in a solid state. Here also it is a solid state. For delta or alpha also it is in solid state. All please come on the time because it will take some time to admit you. It will be distraction for us. Okay. And in between this gamma and this liquid, if certain temperature and certain composition is getting, so scientist has got gamma plus liquid phase. So here this portion, not completely solid, not completely liquid, they have got some mixed composition, or sorry, mixed phase, that is a gamma plus liquid, that means solid plus liquid. Here also one liquid plus Fe3C. So what is that Fe3C? Fe3C is generally called as a cementite. It is also one phase present here. Till now we have seen three solid phases, that is alpha ferrite, gamma austenite, delta ferrite, and one liquid phase, that is liquid L, that is of liquid phase of your alloy, and that alloy is iron carbide, iron and carbon. Now whatever this Fe3C is there, Fe3C, that is again under a solid condition, that is also a solid phase or solid solution, and that solid solution is in solid state, Fe3C, iron carbide. So in many areas you can observe here gamma plus Fe3C, here liquid plus Fe3C, that means liquid plus solid. Here gamma plus Fe3C means solid plus solid. Here also alpha plus Fe3C is there, alpha plus Fe3C, that means solid plus solid. One more, we will see alpha plus gamma, sorry, alpha plus gamma, that means again solid plus solid. Again here is liquid plus delta. In this portion it is liquid plus delta, liquid plus delta, that means liquid phase plus solid phase. Here one more phase is there, that is a delta plus gamma, that means solid plus solid. So like that, different phases we are getting for different temperatures and for different composition of iron carbide. So those we are studying in iron carbon diagram, equilibrium diagram or phase diagram. So these parts we have divided into few three transformations. Firstly, we have seen what are the different solid solutions here: alpha ferrite, gamma austenite, and delta ferrite. One more, that is in the liquid phase of that iron carbide, and one more phase, that is Fe3C. Fe3C is present in the form of solid solution or solid phase. So 1, 2, 3, 4 solid phases are there and one liquid phase. Completely uniformly or unanimously 4 phases are present. Those are different 5 phases, sorry, 1, 2, 3, 4, 4 solids and one liquid. And sometimes their combination is also present. So these things we have to see. So these 5 phases are present here, 4 solid states and 1 liquid state, and sometimes their combination is also present in the diagram. So that we are studying. These things we have divided into 3 transformation. Through 3 transformation we are studying this iron carbon diagram, and these 3 transformations are: first block I have drawn like this. So this block is for peritectic transformation. Peritectic transformation. Second block I have drawn like this. So in that block one more transformation is there, that is eutectic transformation. Here also certain changing phases will be there as temperature decreases. For the constant temperature, during constant temperature it is occurring. Now one more transformation we have drawn one block for that, and that transformation is eutectoid transformation. Eutectoid transformation, this one. Through these three transformation, we are studying the different phases present in this iron carbon diagram. Understand? So first transformation we have seen yesterday, that is a peritectic transformation. Peritectic transformation. In that peritectic transformation, one solid plus liquid is giving another solid S2. S1 plus L is giving S2. Now here in first upper block, you can observe it is at higher temperature and lower percentage of carbon inside the iron. So these percentage, whatever present in that transformation, during that transformation are very low, 0.1%, 0.18% of carbon, 0.55% of carbon, but the temperatures are very high. Those temperatures are nearly 1539, which is the melting point of that pure iron, 1400 degrees Celsius, 1492 degrees Celsius. At 1492 degrees Celsius and percentage of carbon present 0.1, the phase of this iron carbide will be solid, and that solid we are calling it as a delta ferrite. Understand? At 1492 and percentage of carbon 0.1 inside the iron, the phase will be solid, that we are calling as delta ferrite. And at 0.55% of carbon and at same temperature 1492 degrees Celsius, the phase of that iron carbide will be liquid, because above this all phase will be liquid. Again, less than this percentage of carbon and above certain temperature, again that will be phase solid, that is delta. So if you consider this constant temperature 1492 and the percentage is varying of the carbon, 0.1% it will be solid, 0.55% it will be liquid. At that point, there will be some transformation of these one solid and one liquid if they are combined. So you can observe here at this point. So at P point, what has happened? At P point, one liquid and one solid are combined to get another one solid at this P point. So whenever percentage of carbon has got 0.18, so these one solid and one liquid has converted into another solid, and that solid is nothing but a gamma astenite. We have called this gamma as a gamma astenite. Delta ला काय म्हणलो होतं आपण? Delta ferrite. Alpha ला काय म्हणलो होतं? Alpha ferrite only. Isn't it? Alpha ferrite, delta ferrite, gamma astenite, and cementite or iron carbide. Those four phases are in the solid condition, and one liquid condition is present, that is a iron carbide. एकच लिक्विड फेज आहे आणि सॉलिड फेजेस मात्र किती आहेत या डायग्राम मध्ये? चार सॉलिड फेजेस आहेत. एक डेल्टा फेराइट, अल्फा फेराइट, गॅमा ॲस्टेनाइट आणि एक सिमेंटाइट. त्याला आपण Fe3C म्हणलं या डायग्राम मध्ये. हियर Fe3C, isn't it? So these four phases solid and one liquid phases are there. So here for peritectic transformation जे हायर टेम्परेचरला होत होतं त्या डायग्राम मध्ये हा फर्स्ट ब्लॉक आपला. So there one solid, this solid delta ferrite, one liquid has combined at a constant temperature to give one more solid, that is a gamma ferrite, sorry, gamma astenite. For gamma we are calling it as astenite, for delta and alpha we are calling it as a ferrite. Okay, and that delta is for the carbon content up to 0.1%, and that liquid is from 0.55% of carbon, and gamma is having 0.18% of carbon. In the diagram also you can observe for delta here, for M point percentage of carbon is 0.1. For wait a minute, am I audible? Am I audible? Please respond.
Yes, sir.
Okay. Okay, so at m point solid phase is there plus liquid phase at n point. They have given one phase solid phase, that is gamma, because from this p point all the phases here present below this p point will be solid phase, and that solid phase is a gamma astenite. So this transformation at constant temperature is called as a peritectic transformation. Peritectic transformation. Understand? So from this constant temperature, if you reduce the small amount of temperature, then there will be change in the phase. The solid and liquid phase combine होऊन एक common solid phase मिळेल तुम्हाला. Now you may say that इथं एक branch निघाली आहे आणि या साईडला एक branch निघाली आहे. So what are these two branches? So these two branches are, suppose the percentage of carbon is in between 0.1 to 0.18. याच्यामध्ये जर percentage of carbon असेल, in that case, and then we started to cool, so there we have got one more phase, and that phase is delta plus gamma. म्हणजे दोन solid मिळतात, delta plus gamma. Only two solid phases we have got. And if that percentage of carbon is from 0.18 to 0.55 present there, then we are getting different phase, and that different phase is a gamma plus liquid. That different phase is a gamma plus liquid. Now, what is that gamma plus liquid and delta plus gamma is called? Now, that is this portion, this branch from for left side, that is delta plus gamma written here. This delta plus gamma is called as a hypoperitectic steel. Hypoperitectic steel, and here this portion is called as a hyperperitectic transformation. You will see just transformation, not steel. आत्ताच आपण स्टील आणि कार्बाइड कास्ट आयर्न म्हणणार नाही. Afterwards I will tell you. I will say this transformation as a hypoperitectic transformation, and this transformation we will say is a hyperperitectic transformation. And at P point, that means at the percentage of carbon, if there is a 0.18% only, then it will completely transform into another one solid, that is a gamma astenite, and that transformation we are calling it as a peritectic transformation. So understand, if percentage of carbon is exactly 0.18, that will be peritectic transformation. Percentage of carbon is between 0.1 to 0.18, that will be hypo. Hypo म्हणजे less and hyper म्हणजे more. So easily you can understand this is a hypoperitectic transformation, and this is a hyperperitectic transformation. Hyperperitectic transformation. Now this is a peritectic transformation. For this peritectic transformation, we can also find out at this P point, whenever one solid and one liquid has combined to give another solid, whenever this delta and liquid has combined to give gamma astenite solid, what is the amount of delta and what is the amount of liquid present? What is the amount of delta and what is the amount of liquid present, so that they have given certain amount of gamma astenite? So during that combination, what is the amount of delta and liquid present? So that can be found by one rule called as the lever rule. हा lever rule आपण पाठीमागे बघितला. These things I have already explained yesterday also. Today also we are revising this. कारण पुढे जे आपण बघणार दुसरे transformation, there you can easily understand by comparison. So that's why once again we are revising this. So amount of delta, and delta is which phase? Delta is solid phase. Amount of liquid, it is in liquid phase. Now how to calculate amount of delta? So remember the lever rule. So for lever rule we have considered this m to n horizontal line as one lever, and P point as a fulcrum point wherever transformation occurs. So m is a solid, N is a liquid, M and N are getting mixed to get one solid at P point. So here we can apply the lever rule. Mn is the lever and P is the fulcrum point. This we are assuming. Now M is solid, N is liquid. So percentage of solid if you want to find out, what is the formula? या साईडला लिक्विड आहे, लिक्विडचा आर्म, लिक्विड आर्म लेंथ डिवायडेड बाय टोटल आर्म लेंथ एम एन. लिक्विड आर्म लेंथ कुठली आहे? पी एन. पी एन डिवायडेड बाय टोटल आर्म लेंथ इज एम एन. पी एन डिवायडेड बाय एम एन. यू विल गेट अ पर्सेंट इंटू 100 केलं तर पर्सेंटेज, इंटू 100 यू विल गेट पर्सेंटेज ऑफ सॉलिड फेज. पर्सेंटेज ऑफ लिक्विड, जे लिक्विड आहे ते या साईडला आहे. देन अपोजिट आर्म कुठला झाला त्याचा? एम पी झाला, एम पी. So opposite arm, that means solid phase arm, MP divided by total arm. Total arm is Mn. So that formula for amount of delta, that means solid phase. Delta कुठे? M च्या इथे delta आहे, liquid कुठे? तर N च्या इथे liquid आहे. So amount of delta is equal to arm length Pn. Arm length Pn. Delta पाहिजे असेल तर opposite arm घेतो आपण, आणि लिक्विड पाहिजे असेल तर त्याच्या अपोजिट आर्म एम पी असणार. लेंथ पी एन डिवायडेड बाय टोटल आर्म लेंथ एम एन, आणि लिक्विडसाठी लेंथ एम पी डिवायडेड बाय टोटल आर्म लेंथ एम एन. सो बाय दीज टू फॉर्म्युलाज जस्ट पुट द व्हॅल्यूज. पी एन म्हणजे काय असणार आहे? ह्याची लेंथ 0.55 इथं आहे, बरोबर, आणि या पॉइंटला आहे 0.18. So 0.55 minus 0.18, you will get the length of that Pn divided by total length. Total length you can find out 0.55 minus 0.1, you will get the total length. So that calculation is done here. 0.55 minus 0.18 divided by 0.55 minus 0.1 into 100, you will get percentage of solid phase there as a 82.2%, and that solid phase is delta Faraday. Amount of liquid, अगेन अपोजिट आर्म, लिक्विडची पहिला म्हणजे इकडची आर्म घेणार एम पी. एम पी म्हणजे या दोनचा डिफरन्स, दॅट मीन्स 0.18 मायनस 0.1, यू हॅव गॉट दिस लेंथ डिवायडेड बाय टोटल लेंथ. टोटल लेंथ इज दिस टोटल लेंथ एम एन, 0.55 मायनस 0.1. सो into 100 you will get 17.8%. that is the amount of liquid present in that peritectic transformation. Okay, and also we have already studied, after this lever rule you can say for hypoperitectic steel what is occurring? Delta plus liquid is giving as a delta plus gamma, and for hyperperitectic steel, that means hyper, that means more than 0.18, delta plus liquid is giving gamma plus liquid. The same reactions are written, those are also occurring at constant temperature. And hypoperitectic transformation is occurring whenever in that steel or in that iron, just say in that iron percentage of carbon is less than 0.18. Hyperperitectic transformation is occurring whenever in that iron carbon content is less than 0. It should be more than. Here it should be more than. If the carbon content is more than 18%, because from here to here hyperperitectic transformation is occurring from P to N. So for hyper, the percentage of carbon should be more than 0.18. Okay. So this peritectic transformation is occurring at a high temperature. 1492 is a very high temperature. That's why in many cases, if you want to achieve these phases, that is a gamma austenite or delta plus gamma or gamma plus liquid, so these phases are also having certain application, because I have already told you these phases are having different structure, microstructure, and as microstructure changes, property changes. So through this heating, cooling, and getting the new microstructure, we are actually achieving the different properties of same alloy, because here alloy is iron and carbon mixture. So for same mixture, we are getting different properties. Why it is possible? Because we are getting different microstructure for different composition and for different temperatures. So it is at higher temperature. That's why it is having very few applications. In many applications, we need not to increase the temperature up to this, because we are heating that iron carbide at certain low temperature below this. That's why it is having very few applications. So periodic transformation not too much, uh, not that much applicable, or we are applying in the industry or for the any applications. Next transformation in that iron and carbon diagram, इथं आपण बघितलं हा पहिला ब्लॉक झाला पेरिटेटिक ट्रान्सफॉर्मेशनचा. इथले फेजेस आपण सगळे बघितले. बरोबर. आता आपण दुसरे बघू, हा एक ब्लॉक बघू, दॅट इज अ युटेक्टिक ट्रान्सफॉर्मेशन. सॉरी, युटेक्टॉइड सेकंड घेतलाय. युटेक्टॉइड, दॅट मीन्स this eutectoid transformation, we will see all phases present here in this block. So eutectoid transformation we will say now. So in eutectoid transformation, one solid and another one solid are getting combined to give another one solid. It is happening at again constant temperature. So two solids are combining to give a one more solid. S1 plus S3, sorry, S1 plus S2 is giving one more solid. So if you apply these to this phase diagram, so what will be eutectoid transformation in the iron and carbon diagram? Gamma austenite, sorry, yes. So if you are heating, then two solids will get combined, to give one more solid. So that is a eutectoid transformation. So here these two solids combining are alpha ferrite and Fe3C. Fe3C, we are calling it as iron carbide or simply as a cementite. We can say Fe3C as a cementite also, or we can say iron carbide. So iron carbide, I already told you, this is in the solid phase. Alpha ferrite is also in the solid phase, and gamma austenite is also in the solid phase. So here two solids are combining to give one more solid. This transformation is called as eutectoid transformation. Now at certain temperature 727, below this temperature, the phase present in that alloy is a solid phase, and that solid phase contains alpha ferrite also and cementite also, or iron carbide also. These two different solid phases are present. And if we heat that above this temperature, then you will get another one solid called as a gamma austenite. Now this alpha ferrite, gamma austenite, Fe3C, cementite, how these are differed, that we have seen in last lecture. Already I have told you, alpha ferrite is having BCC structure, gamma austenite is having FCC structure, delta ferrite is having BCC structure. As the structure changes, also Fe3C is called as cementite. It is also having different structure. It is having complex orthogonal crystal structure. So all these solid phases we have seen in last lecture are having different microstructure. because these are having different crystal structure. So these are having different properties. So in this Eutectoid transformation, two different solids are combining to give different third solid, and these can be differentiated. Why differentiated? Because these three are having different microstructure, different crystal structure. This transformation we are calling as a Eutectoid transformation. So here you can also say while cooling, so this one solid will give you two solids, or while heating, two solids will get combined to give you one more solid, third solid. So here we will write in opposite direction same reaction whenever we are heating, sorry, whenever we are cooling, gamma actinide will give you two solids, alpha ferrite plus Fe3 cementite. Fe3C is called as cementite, alpha ferrite, and gamma we are calling it as gamma actinide. So gamma actinide is these solids. Now, whenever this transformation occurs, again temperature is constant 200, sorry 727, and what is the percentage of carbon is also important. So याच्यामध्ये आपण बघितलं these percentage of carbon are important. Here also percentage of carbon for this gamma, the diagram you can also observe this gamma must be 0.8% carbon present here. And then if you constant temperature this transformation start, त्याच्यापासून खाली cool केलं, you will get two different solids. So this percentage of carbon is 0.8% for this gamma. Percentage of alpha present in that transformation, percentage of carbon for that alpha will be 0.025%. 0.025%. See here, 0.025. At this D point, phase will be alpha ferrite, and that is solid phase. Solid phase. पूर्ण या साइडला हॉरिझॉन्टल D2 या साइडला जी लाईन असेल, complete diagram 0.025 from this point D point to up to end F point. At this F point, what will be phase? Here will be again solid phase, and कुठली phase असेल तरी Fe3C असेल, Fe3C, and total phase present from this point, this dotted line, or 0.025% to 6.67%, this total horizontal line, the phase present will be alpha plus Fe3C. आणि ह्याच्या एका टोकाला F पॉइंटला कुठली फेज असेल तर Fe3C असेल, बरोबर, Fe3C आयन कार्बाइड, आणि ह्याच्या दुसऱ्या टोकाला म्हणजे डी पॉइंटला कुठली फेज असेल, अगेन सॉलिड फेज, and that will be alpha ferrite, and that percentage of carbon in that alpha ferrite is having 0.025, and percentage of carbon in the F point, that means at the Fe3C cementite, percentage of carbon will be 6.67. 6.67. That's why in that reaction, the percentage of carbon for Fe3C is shown as a 6.67% of carbon. 0.8% of carbon for gamma actinide, 0.025% of carbon for alpha ferrite, 6.67% of carbon for Fe3C cementite. So these are the percentage of carbon. Below that, structure is also shown, represented. What is the crystal structure of these three phases? Because these all three phases are solid, but still they are having different structure, crystal structure, microstructure. That's why they are having different properties. Alpha ferrite is having BCC structure, gamma actinide is having FCC structure, Fe3C cementite is having orthogonal or orthorhombic crystal structure. Now, in MCQs, these structures as well as the percentage of carbon is asked many times. So just remember this percentage of carbon for different transformation. युटेक्टॉइड मध्ये कुठल्या फेजला कुठलं पर्सेंटेज आहे प्लस त्या फेजला कुठलं स्ट्रक्चर आहे. सो दीज थिंग्स मस्ट बी नोन टू यू फॉर मल्टिपल चॉइस क्वेश्चन पर्पज. अंडरस्टँड? नाउ for this again we can apply the lever rule because D to here E point, या E point पर इकडे E point है. I think in that larger diagram also you can see for F point it is from D to F we will apply the lever rule. Fulcrum is E point. Fulcrum is E point because at this E point transformation is occurring. Gammaचं conversion अल्फा प्लस Fe3C मध्ये होतं किंवा हिट करताना दोन सॉलिड अल्फा प्लस Fe3C चं कन्वर्जन गॅमा ॲस्ट्रोनाइट मध्ये होतं at this E point. That's why E is a fulcrum point. Here eutectoid reaction is occurring. That's why we will apply lever rule to DEF point. DEF point ला lever rule apply करू and we will get the percentage of different solids. कारण इथं दोन सॉलिड आहेत, आता लिक्विड आणि सॉलिड नाहीये. कुठलं कुठलं सॉलिड आहे? Amount of ferrite we can find out and we also we can find out amount of cementite. Amount of ferrite and amount of cementite we can find. Now how to calculate amount of ferrite? मोठे डायग्राम बघू आपण. In this diagram, amount of ferrite. Ferrite is in this side alpha ferrite. So opposite arm divided by total arm. Opposite arm will be EF. EF arm length जी आहे इथून या E point पर्यंतची, that divided by total arm. Total arm length will be from this point to this point. Total arm. D point पासूनची F point पर्यंतची arm length will be total arm length. And E point to F point will be opposite arm length for the alpha ferrite. So percentage of ferrite or amount of ferrite will be arm length EF divided by total arm length DF. And for amount of cementite साठी तोच lever rule जर अप्लाय करत झाला म्हणजे इकडच्या साईडचा जो सॉलिड फेज आहे त्याची अमाऊंट काढायची असेल तर अपोजिट आर्म विल बी, कारण F या साईडला आहे सॉलिड फेज, तो सिमेंटाइट या साईडला आहे, त्याच्या अपोजिटचा आर्म कुठला झाला? या फल्क्रम पासून इकडचा. दॅट मीन्स E to D. E to D arm length divided by total arm length DF. DF will be total arm length and opposite arm length is the DE. So DE divided by DF. Same is there. Arm length DE divided by total arm length DF. So just apply this lever rule, put the values. Arm length EF कशी काढणार? आता पहिल्यांदा जर आपण हे काढत असो कुठला अमाऊंट ऑफ फेराइट, फॉर अमाऊंट ऑफ फेराइट arm length EF divided by arm length DF. EF कशी काढणार? EF, so percentage of carbon in EF is 6.67 minus percentage of carbon at this E point is 0.8. At E point percentage of carbon is 0.8. So 6.67 minus 0.8 will be arm length EF. And total arm length D to E. So 6.67 minus 0.025 because at D point percentage of carbon is 0.025. So just put the values 6.67 minus 0.8, 6.67 minus 0.008. So into 100 will get in the percentage and this percentage is coming 88.1. हे percentage लक्षात ठेवायची गरज नाही. Just remember the reaction which is occurring for that transformation. Percentage of carbon. Easily you can apply this lever rule and find out this percentage. The percentage MCQ ला विचारत नाहीत. This calculation is not expected, but you know the lever rule, you can write in the theory. MCQ साठी सुद्धा हे important नाही. Just remember the formula for MCQ. Not these percentage. Exact value of percentage is never asked. Percentage of carbon may ask in those transformation. Okay. So like this we have found. Now one more term here is written, that is term is written here. Ferrite plus cementite. Ferrite means what? अल्फाला म्हणतो आपण अल्फा फेराइट आणि सिमेंटाइट कोणाला म्हणतो Fe3C ला म्हणतो. So alpha plus Fe3C, ferrite plus cementite are giving what? Gamma austenite. Are giving gamma austenite. These three are different phases, but in this diagram observe that here gamma phase is there and here one phase, different phase. इथं अल्फा आहे आणि या साईडला कोण आहे Fe3C आहे. पण त्या दोन्हीच्या मध्ये अल्फाच्या आणि Fe3C मध्ये जेव्हा सॉलिड फेज यू हॅव गॉट, दिस सॉलिड फेज यू हॅव गॉट एज अल्फा प्लस Fe3C. दोन सॉलिड कंबाईन स्टेट मध्ये आढळले. Correct. Those are not homogeneously mixed, but those are different solids present in that alpha plus Fe3C. So whenever such combination you are got, so that combination can also be called as a perlite. Perlite. In our वेगळे तुमच्यासाठी, but still remember these names in oral or whenever you are studying in the metallurgy for higher studies or for your project in further. So these names are very much important. In every literature you will find these names. ह्या नावाचा अर्थ काय? So you must know. So perlite. Perlite is nothing but a ferrite plus cementite. इथून पुढे कधी परलाइट हा शब्द आला, परलाइट, परलाइट म्हणजे कुठली फेज या डायग्राम मधली? ही खालची फेज की ज्याच्यामध्ये दोन सॉलिड प्रेझेंट आहेत सॉलिड फेज मध्येच. आणि ते सॉलिड कुठले आहेत तर फेराइट आणि सिमेंटाइट. फेराइट अँड सिमेंटाइट. अँड सिमेंटाइट इज व्हॉट? Fe3C. फेराइट इज व्हॉट? अल्फा फेज. सो अल्फा प्लस Fe3C, फेराइट प्लस सिमेंटाइट is nothing but perlite. This eutectoid mixture of ferrite and cementite is called as a perlite due to its pearly appearance under the optical microscope. So in under microscope, if you study, if suppose this is the circular specimen, in that specimen you will see the circular shaped microstructure inside the specimen, and these are just appearing like a pearls. मोत्यासारखे दिसतो. That's why the name is given for that as a perlite. Perlite. Just remember this, ferrite plus cementite can also be called as a perlite. हे देतंय असं नाही, बरोबर. हे फेराइट प्लस सिमेंटाइट परलाइट देतं असं नाही. त्या दोन्हीच्या अपीअरन्सला काय म्हणतो आपण? परलाइट. That mixture we are calling as a perlite. So this is regarding eutectoid transformation. या मेन डायग्राम मधला आपल्या पहिलं ट्रान्सफॉर्मेशन पेरिटेक्टिक we have seen. Then we have seen eutectoid transformation. Now we will see eutectic transformation, third transformation. हे ट्रान्सफॉर्मेशन बघतोय म्हणजे आपण फेजेसच बघतोय ह्या डायग्राम मधल्या, बरोबर आहे. ऑल फेजेस वी आर स्टडिंग. सो थर्ड transformation in this diagram is there, that is a eutectic transformation. Eutectic transformation eutectic transformation. Now in eutectic transformation, you know that you have seen while studying the cooling curves, you have seen one type of cooling curve, that is cooling curve for eutectic solid solutions. Eutectic solid solution. त्याच्यामध्ये तुम्ही बघितलं होतं on one line, on one horizontal line, two different solids are present. So liquid is converted while cooling into two solids, S1 and S2. This transformation is the eutectic transformation. That means one liquid will give you two different solids while cooling. So at constant temperature, that liquid get converted into two solids. ह्या डायग्राम मध्ये कुठे मेन डायग्राम मध्ये iron and carbide. So here, so this is a liquid phase. 1 minute. Okay, it will be, here is a one liquid phase. So that liquid phase of that iron and iron carbide is cooled at constant temperature. So whenever that got a temperature 1147, it has started to convert into solid phase. But those two solid phases will be there, and those two solid phases will be different. आणि त्या फेजेस कुठल्या असतील तर एक गॅमा असेल, त्या गॅमाला आपण काय म्हणतो, गॅमा ॲस्टेनाइट म्हणतो. लक्ष ठेवा, अल्फा फराइट, डेल्टा फराइट, गॅमा ॲस्टेनाइट आणि Fe3C ला काय म्हणतो, सिमेंटाइट. Fe3C सिमेंटाइट. So gamma austenite plus cementite, austenite plus cementite. These two solid phases you will get at this temperature 1147 from one liquid. So this transformation is called as a eutectic transformation. Eutectic transformation. आता मगाशी जे झालं युटेक्टॉइड ट्रान्सफॉर्मेशन, त्याच्यामध्ये एक गोष्ट सांगायची राहिली माझी. जसं पेरिटेक्टिक ट्रान्सफॉर्मेशनला हे दोन आर्म निघाले होते, या साईडला एक आणि या साईडला एक. तर पीच्या या साईडला पर्सेंटेज ऑफ कार्बन वेगळं होतं, किती होतं, 0.18 पेक्षा कमी होतं. म्हणून आपण त्याला काय म्हणलो, हायपोपेरिटेक्टिक ट्रान्सफॉर्मेशन. आणि पर्सेंटेज ऑफ कार्बन फ्रॉम 0.18 पेक्षा जास्त होतं या राईट हँड साईडला P2N कडे. त्यामुळे आपण त्याला ट्रान्सफॉर्मेशनला काय म्हणलो, हायपर पेरिटेक्टिक ट्रान्सफॉर्मेशन. सिमिलरली in this eutectoid transformation also we can say two hypo-eutectoid transformation is there and hyper-eutectoid transformation is also there. Hypo कधी म्हणणार, पर्सेंटेज ऑफ कार्बन 0.8 लागतं कुठं, ई पॉइंटला, त्याच्यापेक्षा कमी असेल तर दॅट विल बी कॉल्ड एज अ हायपो-eutectic, eutectoid, hypo-eutectoid transformation. And if it is more than this E point, it will be called as a hyper-eutectoid transformation. Hypo-eutectoid and hyper-eutectoid transformation. जसं हायपर आणि हायपोपेरिटेक्टिक होतं, तसंच इथं हायपर and hypo-eutectoid transformations are there. Similarly here also for eutectic transformation, if that percentage of carbon at point U is 4.3, त्याच्यापेक्षा कमी असेल, then that transformation will be called as a hypo-eutectic transformation. आणि याच्यापेक्षा जास्त असेल पर्सेंटेज ऑफ कार्बन, कारण इथून बघा लिक्विड ह्याच्यापेक्षा खाली येणारच आहे, इकडं लिक्विडचं कन्व्हर्जन दोन सॉलिड मध्ये होणारच आहे. बट if percentage of carbon is more than this, then that will be called transformation hyper-eutectic transformation. Hyper-eutectic transformation. So these, remember just hyper and hypo. Hypo म्हणजे कमी, hyper म्हणजे जास्त. Now eutectic we are seeing now. One liquid is getting converted into two solid, and that liquid is L. That liquid is having percentage of carbon 4.3% of carbon. In the diagram again we will see. इथं लिक्विडचं पर्सेंटेज किती आहे, त्या U पॉइंटला 4.3%. दॅट इज कन्वर्टेड इन टू सॉलिड. टू सॉलिड कुठले, त्यातला एक गॅमा आहे आणि एक आहे Fe3C. गॅमाचं पर्सेंटेज या साईडला किती दिसतंय तुम्हाला, 2% दिसतंय, बरोबर. कारण हे हॉरिझॉन्टल लिव्हर रूल अप्लाय करायचं आपल्याला, एक लाईन हॉरिझॉन्टल ड्रॉ करायची, त्या लाईन वरती इथं J पॉइंट आहे आणि या साईडला एक काहीतरी नाव द्या त्या पॉइंटला. So at J point percentage of carbon is 2, at U point percentage of carbon is 4.3, and here given any name, suppose X name is given at this X point, but the percentage of carbon it is 6.67, JUX. So for this horizontal line, again you can apply lever rule to get the percentage of two different solids. कारण दोन सॉलिड मिळत आहेत. हा पहिला सॉलिड कुठला आहे, गॅमा ॲस्टेनाइट या J पॉइंटला. X पॉइंटला दुसरा सॉलिड कुठला आहे, Fe3C, तो आहे सिमेंटाइट. मग सिमेंटाइटचं पर्सेंटेज किती अँड गॅमाचं पर्सेंटेज किती, दॅट वी कॅन फाइंड आउट बाय युजिंग अगेन लिव्हर रूल. Hello, any problem? Problem? जस्ट म्यूट करा. कोणाचा तरी आवाज चालू आहे. जस्ट म्यूट इट. Okay. So amount of ferrite and amount of cement. Sorry, here amount of perlite and amount of cementite. Now here. So from this J point to X point, if you want to apply the lever rule, so the percentage of solid phase present here at the J and percentage of solid phase present here at X, you can apply the lever rule. But solid present towards this left side, will be not only this gamma. त्याच्या खाली जर बघितलं तुम्ही इथून खाली, because at this temperature lower than this 727, what is the phase here? Alpha plus Fe3C is present, and on this side totally here Fe3C is present, extremely right hand side, and towards the left it is alpha plus Fe3C. That's why two solid phases present in that eutectic transformation will be, we can say, not only alpha, we can also say it as a, again I will say in the diagram, alpha plus Fe3C also. लक्षात मी काय म्हणतो, at this J point definitely you are getting one solid phase, that is a alpha, sorry, gamma. But at lower temperature solid phase is there, but different solid phase, that is alpha plus Fe3C. Alpha plus Fe3C पण present आहे इथे, isn't it? Not only gamma plus Fe3C, gamma या साइडला, Fe3C या साइडला, but below the same transformation, eutectic transformation, these different phases are also there, alpha plus Fe3C. So that's why that alpha plus Fe3C already we have seen, alpha plus Fe3C, that means ferrite plus cementite, we can also call it as a perlite. Alpha plus Fe3C, we can also call it as a perlite. So perlite can also be one solid phase present there. So that's why while calculating this percentage of different solids, we can find amount of perlite and amount of cementite. We can no doubt find out amount of gamma austenite present here at J point and amount of cementite present at this X point. That also we can find out. But at lower temperature, alpha plus Fe3C is also present under the same transformation. So alpha plus Fe3C is called as a perlite. So amount of that perlite also we can find out by using lever rule. So that lever rule we will see. Now eutectic transformation, for this eutectic transformation, austenite and cementite, that means alpha plus Fe3C, whatever it is present, that we can call it as a ledeborite. जसं पाठीमागच्या ट्रान्सफॉर्मेशन मध्ये eutectoid मध्ये ferrite plus cementite, हा जो अल्फा ferrite आणि हा जो cementite होता, for that we are call it as a perlite because of the pearly shape appearance in the microstructure. We are called it as cementite plus ferrite as a perlite. Similarly, whatever this gamma austenite and Fe3C cementite is called as a ledeborite. मग परत कधी जर शब्द आला ledeborite, that ledeborite is you have seen in the eutectic transformation, and that ledeborite is nothing but austenite plus cementite. आणि perlite म्हणजे काय, तर perlite म्हणजे ferrite plus cementite. Ferrite plus cementite is a perlite, austenite plus cementite is a ledeborite. two different solid phases combinedly. We can say this as a ladeborite. Here we can see these two different phases combinedly as a perlite. So perlite and ladeborite. These two things, just remember the names, because in further in microstructure we may say this ladeborite is occurring or observing that ladeborite is nothing but austenite and cementite. We may say this is a perlite, so perlite is nothing but ferrite plus cementite. So these three transformations we have seen: peritectic transformation, eutectic transformation, and eutectoid transformation. So these are important. Through this, we have seen various phases. We have also applied lever rule to get the different percentage of phases. Also, we have seen hypoeutectic, hypereutectic, again hypoeutectoid, hypereutectoid, hypoperitectic, and hyperperitectic transformations. So these all things are very important, and how to draw exactly this phase diagram that we will see afterwards. But just you have understood now different transformation, different phases present in that phase diagram. Is it understood? Is it understood?
Yes, sir.
Just reply in the chat. Reply in the chat. Don't leave the meeting. I have to take the attendance. I'm taking attendance now. Call your roll numbers. Number
Yes, sir.
one, two,
Present.
three. Wait a minute, I will share my screen so that